Okay, so in this week's class we're going to start complex numbers. Now there's a couple of videos that I had made for the higher level students in complex numbers, and what we do in the start of the higher level course is exactly the same as what we do in the ordinary level course. So throughout this video you might hear me mentioning that it's higher level, but everything I'm about to show you here, I'm editing out the bits that you don't need and I'm just giving you the stuff that you need at ordinary level. So regardless of the fact that I might be mentioning higher level at some points, I want you to work through it because everything I'm going to show you in this video is in fact ordinary level complex numbers. In this video, I want to introduce you to complex numbers. Okay, so first of all, in every other topic in maths in the Leave Insert, we deal with real numbers. But every so often we come across what are known as imaginary numbers. When we come across imaginary numbers, that's where complex numbers come into play. The principle behind complex numbers, it's all built upon the fact that I is equal to the square root of -1. You should remember from junior cert that if I was teaching junior certs and they get to a stage where they have the square root of a negative number, I'll tell them they've made a mistake. Because you cannot have a negative number in the square root without ending up with an imaginary number. This is not a real number. The square root of -25 is not real, and the square root of -36 is not real. However, when we're dealing with complex numbers, we can simplify this. You could rewrite the square root of -9. That's the same as the square root of -1 multiplied by the square root of +9. So if you just split up, if you know your rules from surds, the square root of -9 is the same as the square root of -1 times the square root of 9. I know that because -1 multiplied by 9 gives me -9. And now I know that the square root of 9 is 3, and I know the square root of -1 is I. Okay? In complex numbers questions, in the question it usually states that I is equal to the square root of -1. In other words, if I simplify the square root of -9 fully, I get 3i. 3i, and I stands for imaginary. So 3i is an imaginary number. Now I know the principle is very abstract, but basically it's just built upon that. You could do the same thing with the square root of -25. The square root of -25 is the same as the square root of 25 multiplied by the square root of -1. The square root of 25 is 5, and the square root of -1, as always, is just I. So the square root of -25 can be simplified down to 5i. I can do the same thing here. The square root of -36 is the same as the square root of +36 times the square root of -1. The square root of 36 is 6, and the square root of -1 is I. So this is where imaginary numbers come into play. And while we're studying complex numbers for this entire topic, we're going to have i's and we're going to have real numbers, but we're also going to have i's. So 5i, 6i, 3i, they're known as imaginary numbers. All the numbers we deal with in other topics, 5, 6, 3, 2, whatever it is, they're real numbers. So complex numbers usually contain a real element and an imaginary element. So let me give you an example of complex numbers. Most complex numbers can be written in the form of a plus bi. For example, 6 plus 5i. 6 plus 5i is a complex number. This is known as a complex number because it contains a real value, a real number, and it contains an imaginary number. 6 is a real number. Obviously, we've been dealing with that for years. 5i is an imaginary number. So 6 plus 5i, that's a real element and an imaginary element. That is known as a complex number. A complex number has both real and imaginary elements to it. And in fact, every number that you've ever come across can be written in the form of a complex number. Let's just take any random number like 10. Let's say the number 10. You could write this as a complex number because 10, obviously that's a real number, but I could write that as 10 plus 0i. 10 plus 0i is in the form of a complex number. So every real number can actually be written in this form where you just add in a 0i. And that's where complex numbers come into play, a real element and an imaginary element. So now let's just explore a few more complicated aspects to your complex numbers. Okay, so another thing we need to look at here is complex numbers is built upon the fact that I is equal to the square root of -1. Imagine what would happen if I squared both sides here. If you square the left hand side, you end up with minus 1. If you square the right hand side, you end up with I squared. So if I'm saying that I is equal to the square root of minus 1, it follows that that means that I squared is equal to minus 1. If you just square the right hand side and square the left hand side, I squared is minus 1. So in any question, if we're dealing with complex numbers and you end up with an I squared, you sub in a minus 1. Based on this now, you could get something like, sometimes they give you questions where you have I to the power of 11, and you might have to simplify that down. Well, first of all, I to the power of 11 could be rewritten as I to the power of 10 multiplied by I to the power of 1. Okay, and the I to the power of 10 is useful to me, because if I split the I to the power of 10 up, I could say that that's I squared to the power of 5. I squared to the power of 5 is the same as I to the power of 10, because 2 multiplied by 5 gives me 10. And then I just have an I to the power of 1 out here. Now, from what I'm just after telling you, I know that I squared is equal to minus 1, which means that I squared to the power of 5 is minus 1 to the power of 5, multiplied by I to the power of 1. So minus 1 to the power of 5, that's 5 minuses, and if you have an uneven amount of minuses, overall it will end up being negative. A minus by minus by minus by minus by minus ends up as a minus 1. So minus 1 to the power of 5 just ends up as minus 1 multiplied by I. So you might be asked to just simplify something like that. That's my final answer. I to the power of 11 can be simplified down to minus 1 times I. So with that in mind, I'm going to give you 3 questions now that I want you to try. So I want you now, using the same logic, to simplify I to the power of 50, I to the power of 21, and I to the power of minus 12. Okay, so based on that logic, I to the power of 50, it's already even, so I don't need to split up the powers. But I can split up I to the power of 50 as I to the power of 2, all to the power of 25. So I squared to the power of 25. Remember, I want to break it down to I squared because I know that I squared is equal to minus 1. So I can substitute in a minus 1. And I know that it's 2 and a 25 because 2 multiplied by 25 gives me 50. So I can rewrite I squared to the power of 25 as minus 1 to the power of 25. Now if you're multiplying a minus by itself 25 times, that's an odd amount of minuses, so it's going to end up as a minus. So your final answer there will be minus 1. Now for part B, I asked you to simplify I to the power of 21. Again, you have to split up the powers so that one of them is even. So I split it up. I to the power of 21 is the same as I to the power of 20 multiplied by I to the power of 1. I to the power of 20 simplifies down to I squared to the power of 10, and I've left the I to the power of 1 as it is. And I can now say that that is equal to, and instead of the I squared, I just subbed in a minus 1. So I squared to the power of 10 is the same as minus 1 to the power of 10, and then there's an I at the end. Minus 1 by itself 10 times, that's an even amount of minuses, which means you end up with a plus. Minus by minus 10 times gives me plus 1 times I. Now the last one was a bit trickier. I've given you I to the power of minus 12. You should go to page 21 in your maths tables. The fifth rule of powers in your maths tables says that a to the power of minus p is the same as 1 over a to the power of p. With this rule in mind, I can simplify I to the power of minus 12. I could rewrite that as 1 over I to the power of plus 12. And now I'm happy out, at least I no longer have a negative power. Now if I wanted to simplify the bottom there, that's the same as I to the power of 12 is the same as I squared all to the power of 6. Because 2 multiplied by 6 gives me 12. Now all I need to do is substitute in, instead of I squared, I can just sub in a minus 1. So this simplifies down to 1 over minus 1 to the power of 6. And now to finish that one off, the bottom is minus 1 to the power of 6. That's a minus by minus by minus to 6 minuses, which is an even amount of minuses, which means it ends up as a plus. So you'll just actually end up with 1 over 1. Obviously 1 over 1, your final answer there is just plus 1. So that's just playing around with the powers. Obviously I could give you I to the power of a million or I to the power of a billion or whatever, but either way you just split it up following that same logic. Now that's all I wanted to talk to you on your introduction to complex numbers. Let's move on now. If you watch our next video, we're going to be adding, subtracting and multiplying complex numbers. Okay, so then what I want to talk to you about in this video is the rules for rectangular form. I alluded to this in the previous video, but you need to be aware that rectangular form is when you write a complex number in the form of a plus bi. The a represents the real element of the complex number, while the bi represents the imaginary element of the complex number. When we're dealing with complex numbers, we usually use the letter z to indicate that it's a complex number. So supposing I gave you a question where they say that z1 is equal to 2 minus 3i and that z2 is equal to 3 plus 5i. That's usually the template they give it to you in. Notice that, so I have two complex numbers in rectangular form. And the first thing I want to talk to you about is addition and subtraction of complex numbers. So the first thing, supposing they asked you to add z1 plus z2, then they asked you to z1 and subtract z2. It's relatively straightforward to do this. If I asked you to get z1 plus z2, that just means you're adding z1 is 2 minus 3i, and you're going to add 3 plus 5i. Okay? In order to add complex numbers together, all you need to do is add the real elements together and add the imaginary elements together. So the real elements in this case are, there's a 2 here and there's a plus 3 here. So just 2 plus 3. The imaginary elements are minus 3i and plus 5i. 2 plus 3 gives me 5. Minus 3i plus 5i just gives me plus 2i. Which means that z1 plus z2, your final answer there would be 5 plus 2i. Notice how your answer is in rectangular form again. Now if we did the same thing for z1 minus z2, well, z1 is 2 minus 3i, and you need to subtract z2, so it's minus 3 plus 5i. Now you just have to be careful with your signs here. We'd have to multiply out this bracket. So I can leave 2 minus 3i exactly as it is. If you multiply minus 1 by the first thing, you'll get minus 3. Minus 1 by the second thing, you'll get minus 5i. And now I need to group my real values, group my imaginary values. So I have a 2 and I've got a minus 3. I can group those together. My imaginary elements are minus 3i, minus 5i. Now if I just add these, 2 minus 3 gives me minus 1. Minus 3i minus 5i gives me minus 8i. So your answer to that one, z1 minus z2, is minus 1 minus 8i. But now, supposing I moved on and I asked you to get z1 multiplied by z2. The dot in the middle, remember, that indicates multiply. So z1 multiplied by z2. In this case, that would be 2 minus 3i multiplied by 3 plus 5i. It's just like algebra. If you're multiplying out if there's two terms in each bracket and you have to multiply them by each other, it's the first term in the first bracket by the second bracket. 2 multiplied by 3 plus 5i. Then the second term in the first bracket by the second bracket. Minus 3i multiplied by 3 plus 5i. So most of this is relatively straightforward. There's just one catch. 2 multiplied by 3 gives me 6. 2 multiplied by plus 5i gives me plus 10i. Minus 3i multiplied by 3 gives me minus 9i. And minus 3i multiplied by plus 5i gives me minus 15i squared. Now, you need to be careful. Remember we said in the previous video that I squared is equal to minus 1. Which means that we have to substitute in, instead of an I squared, I need to plug in a minus 1. So for the moment, I can leave the 6 as it is. I can add the two like terms together. Plus 10 minus 9 gives me plus 1i. And then minus 15i squared becomes minus 15 times minus 1. So in fact, you should realize that if there's a term with an I squared in it, it's a real value. It's going to end up being a real number. The I is eliminated and I end up with a real number. So in fact, this one is just going to be 6. And then minus 15 minus 1 is plus 15. So I can group the 15 with it. And the only imaginary element I have is plus 1i. Now 6 plus 15 works out as 21 plus, and your final answer there is 21 plus 1i. So for multiplication, just be careful. When you're multiplying complex numbers, you'll always end up with a term that has an I squared in it. If you have a term with an I squared in it, you need to substitute in -1 instead of the I squared. Simplify it out and your final answer should be in rectangular form, 21 plus 1i. Okay, so with that in mind, that's our adding, subtracting and multiplying. I want you to try one now. Supposing Z1 is 4 plus 3i and Z2 is 5 plus 3i. I want you to find Z1 plus Z2, Z1 minus Z2, and Z1 multiplied by Z2. So for the first one here, I asked you to get Z1 plus Z2. Z1 is 4 plus 3i, Z2 is 5 plus 3i. So all I did on the second line was I grouped the real numbers, 4 plus 5, and I grouped the imaginary numbers, 3i plus 3i. If we then add them together, 4 plus 5 adds up to 9, 3i plus 3i adds up to 6i. So your final answer there, Z1 plus Z2 is equal to 9 plus 6i. Okay, so for the second one, I asked you to get Z1 minus Z2. Z1 is 4 plus 3i, and then you're subtracting 5 plus 3i. If it's minus 5 plus 3i, that means you end up changing your signs. Minus 1 by 5 is minus 5, minus 1 by plus 3i is minus 3i. If you then group your real numbers, you have 4 minus 5. If you group the imaginary ones, you have 3i minus 3i. 4 minus 5 is minus 1, and plus 3 minus 3 is 0. So notice you should still write your answer as minus 1 plus 0i. Your answer should still be in rectangular form. Often in the exam questions, it will say to leave it in the form of a plus bi, but even if it didn't in this question, you should still leave your answer in rectangular form. Okay, the third one I asked you to do was to get Z1 multiplied by Z2. 4 plus 3i multiplied by 5 plus 3i. So it's the first thing in the first bracket by the second bracket, second thing in the first bracket by the second bracket. 4 by 5 is 20, 4 multiplied by 3i is 12i. 3i by 5 is 15i, and 3i by 3i squared, 3i by 3i is 9i squared. Now you can group the two middle terms here. 12i plus 15i adds up to 27i. And remember, instead of an I squared, you need to sub in a minus 1. So 9i squared becomes 9 times minus 1. Or in other words, plus 9 by minus 1 becomes minus 9. My real elements end up as 20 minus 9, which is 11. So I end up, my final answer is 11 plus 27i. So that's our adding, subtracting and multiplying. Logically, the next thing we need to do is talk about dividing and conjugates. Okay, what I want to talk to you about in this video is, first of all, we need to talk about conjugates, and when we have a good understanding of conjugates, then we can start talking about dividing complex numbers. So supposing you were given Z1 is equal to 3 plus 2i, and you were asked to write down Z1 with a bar above it. That line, or that horizontal line above Z1 means the conjugate of Z1. So I've spelled it out for you here. It says write down Z1 with a line above it, the conjugate of Z1. But usually it won't even give you this bit. It'll just say write down and it'll give you this. A line above Z1 means the conjugate of Z1. And it's incredibly easy to find. If an exam question says write down, that implies you don't have to do any work, that you can just literally just look at it and write it down. If Z1 is equal to 3 plus 2i, then I could answer this one and I could say, right, well, that means the conjugate of Z1 is equal to 3 minus 2i. In order to get a conjugate, you just change the sign of the number in front of change the sign of the imaginary number. So this was a plus 2, means it's going to become a minus 2. So if Z1 is 3 plus 2i, the conjugate of Z1 is 3 minus 2i. Okay, so and now what I want to do is, it's important you understand how useful conjugates are. So in part 2, I've asked you to multiply Z1 by the conjugate of Z1. So I'm going to go through this example and then give you a few more to do. Supposing I was asked to multiply Z1, which is 3 plus 2i, by its conjugate, which is 3 minus 2i. It's the first thing in the first bracket multiplied by the second bracket. And then the second thing in the first bracket multiplied by the second bracket. And let's just multiply this out. 3 by 3 gives me 9. 3 multiplied by minus 2 gives me minus 6i. Plus 2i multiplied by 3 gives me plus 6i. Plus 2i multiplied by minus 2i is minus 4i squared. Now the important thing here, I want you to look at the two middle terms. I have minus 6i plus 6i. So they're going to cancel each other out. That's the usefulness of conjugates. Whenever you have a conjugate, if you multiply a complex number by its conjugate, the imaginary numbers cancel each other out, and you're left with a real number. Minus 6i plus 6i cancel out. And if I simplify this, I get 9, and then minus 4 times I squared is the same as minus 4 times minus 1. Minus 4 multiplied by minus 1 is plus 4, so I actually have 9 plus 4, so your final answer there would be 13. Or you could write it as 13 plus 0i. But the whole point of conjugates is that when you multiply a complex number by its conjugate, the imaginary numbers always cancel each other out. So now I'm happy, I know that Z1 multiplied by its conjugate is just 13. With that in mind, let's practice a few questions. Now I'm giving you Z2 is equal to 3 minus 1i, Z3 is equal to minus 1 plus 2i. I want you to write down the conjugate of Z2 and find Z2 multiplied by its conjugate. I want you to write down the conjugate of Z3 and find Z3 multiplied by its conjugate. So take a minute, pause the video, make sure you go through those, and then I'm going to talk to you about the solutions. The first part, I asked you to write down the conjugate of Z2. If Z2 is 3 minus 1i, then the conjugate of Z2 is 3 plus 1i. All I do is, instead of a minus in front of the imaginary element, I put a plus in front of it. So it's just 3 plus 1i. Part 2, I asked you to get Z2 times the conjugate of Z2. Z2 is 3 minus 1i, the conjugate of Z2 is 3 plus 1i. So it's the first thing in the first bracket by the second bracket, second thing in the first bracket by the second bracket. 3 by 3 is 9, 3 by 1i is 3i. Minus 1i by 3 is minus 3i, minus 1i by plus 1i is minus 1i squared. Now remember, the whole point of this is that the plus 3i and the minus 3i cancel. The imaginary numbers always cancel when you multiply one complex number by its conjugate. And then I can simplify minus 1i squared is the same as minus 1 times minus 1. Minus by minus gives me plus, so I end up with 9 plus 1, which works out as 10. And that's your final answer for part 2. In part 3, I asked you to write down the conjugate of Z3. If Z3 is minus 1 plus 2i, in order to get its conjugate, we just change the sign in front of the I. It becomes minus 1 minus 2i. So the conjugate of Z3 is just minus 1 minus 2i. In the fourth part of the question here, I asked you to get Z3 multiplied by the conjugate of Z3, which is minus 1 plus 2i by minus 1 minus 2i. The first thing in the first bracket by the second bracket, second thing in the first bracket by the second bracket. Minus 1 multiplied by minus 1 is plus 1. Minus 1 multiplied by minus 2i is plus 2i. Plus 2i multiplied by minus 1 is minus 2i. And then plus 2i multiplied by minus 2i gives me minus 4i squared. And now the terms in the middle, the plus 2i and the minus 2i, will cancel each other out. So that means I'm left with a plus 1 here, and the minus 4 times i squared becomes minus 4 times minus 1. Minus by minus gives me plus, so I end up with 1 plus 4, and my final answer there is 5. Now that we've got a good grip on conjugates, we can now start talking about dividing complex numbers. Okay, so now I'm talking about divisibility. We've gotten Z1 and its conjugate and multiplied them by each other. We've gotten Z2 and its conjugate and multiplied it by each other. And we've gotten Z3 and its conjugate and multiplied it by each other. So now I want to address questions where you might be asked to find Z1 over Z2 and leave your answer in the form of A plus BI. So I'm dividing one complex number by another. I'm dividing Z2 into Z1. So if I was to write that out mathematically, Z1 is 3 plus 2i and Z2 is 3 minus 1i. So I've been asked to get 3 plus 2i divided by 3 minus 1i, but I need to simplify it to write it in the form of A plus BI. In these questions, the point is you cannot have an I on the bottom of a fraction. If you have a real number on the bottom of the fraction, then we're grand, no bother. But if you have an I on the bottom of a fraction, that's where we have the problem. So in order to simplify this fraction, you have to eliminate the I from the bottom of the fraction. And in order to eliminate, we've just done 3 examples of that. In order to eliminate the I from 3 minus 1i, I would need to multiply 3 minus 1i by its conjugate. If I multiply the bottom of this fraction by 3 plus 1i, if you multiply 3 plus 1i by 3 minus 1i, you know that you're going to end up with 10. We multiplied that out a minute ago. If you multiply 3 minus 1i by 3 plus 1i, the i's are eliminated. But I can't just randomly multiply the bottom of a fraction by 3 plus 1i. If you multiply the bottom of the fraction by 3 plus 1i, you also have to multiply the top of that fraction by 3 plus 1i. So I'm going to also multiply the top by 3 plus 1i. Because ultimately, look at what I'm doing now. I'm multiplying by 3 plus 1i over 3 plus 1i. If the top of the fraction and the bottom of the fraction are the same, I'm actually just multiplying by 1. So I'm not changing the value of the expression. All I'm doing is I'm multiplying the top by 3 plus 1i and the bottom by 3 plus 1i. The reason being, I know that when I multiply out these bottom ones, I'm going to end up with a real number. So to simplify this, all I need to do is multiply 3 plus 2i by 3 plus 1i, and then 3 minus 1i by 3 plus 1i. So all this boils down to is multiplying out. On the top, I need to multiply 3 plus 2i by 3 plus 1i. I've done that here, 3 plus 2i by 3 plus 1i. If you multiply it out, you end up with 7 plus 9i. The bottom, we've done it previously in this video. You multiply 3 minus 1i by its conjugate, 3 plus 1i. When you simplify it down, you end up with 10. In other words, the top of the fraction just ends up as 7 plus 9i. The bottom of the fraction just ends up as 10. So I had this fraction multiplied by that fraction, simplified fully. The top is just 7 plus 9i, and the bottom is just 10. Now, you usually are expected to separate the real value and the imaginary value. So 7 plus 9i over 10 should be split into 7 over 10 plus 9 over 10i. But obviously that depends on the wording in the question. Usually you're expected to leave your answer like this, where the real value is 7 over 10, the imaginary value is 9 over 10i. So whenever you're multiplying, if you have an imaginary number on the bottom of the fraction, you have to multiply the top and the bottom by the conjugate of the bottom. With that in mind, we're going to use the same values. This is your Z1, this is your Z2, this is your Z3. I want you to try two questions here. I want you to find Z2 over Z1 and leave your answer in the form of A plus BI. Find Z2 over Z3 and leave your answer in the form A plus BI. In each case, you need to multiply top and bottom by the conjugate of the bottom. So I want you to pause the video, try those two questions, and then go through the solutions. So the first one I asked you to do here was to find Z2 over Z1 and write your answer in the form of A plus BI. We're given Z1 as 3 plus 2i and Z2 is 3 minus 1i. So that means that Z2 over Z1 is 3 minus 1i over 3 plus 2i. Now when you have this fraction, you should realize that the immediate complication is the I on the bottom of the fraction. You need to eliminate the imaginary number from the bottom of the fraction. In order to eliminate the imaginary number, we take the complex number on the bottom, which is 3 plus 2i, and we multiply it by its conjugate, which is 3 minus 2i. But you can't just randomly multiply the bottom by 3 minus 2i. In order to compensate, if you're multiplying the bottom by 3 minus 2i, you also have to multiply the top by 3 minus 2i. Because then ultimately all you're multiplying by is 1, which doesn't change the value of the expression. So now to simplify this, it's just multiplication. On the top, it's just 3 minus 1i by 3 minus 2i. I multiply that out here, and it works out as 7 minus 9i. On the bottom, it's just 3 plus 2i by its conjugate, which we did earlier in this video, and it works out as 13. So remember, the whole point of it is so that the i's will cancel each other out, and you're left with a real number. Which means if you multiply this out, I can simplify this and say that the top of this fraction multiplied is 7 minus 9i. The bottom of this fraction multiplied by each other gives me 13. And to leave your answer in the form of A plus BI, we need to split this up. So that means that the real element is 7 over 13. That's the real number. And the imaginary number is minus 9 over 13i. So your final answer, 7 over 13 minus 9 over 13i. That's Z2 over Z1 simplified fully. Okay, and the second one I gave you was to find Z2 over Z3 and write your answer in the form of A plus BI. I told you Z2 is 3 minus 1i and Z3 is minus 1 plus 2i. So first of all, I'm just going to sub into my fraction, and that becomes 3 minus 1i over minus 1 plus 2i. When you have this fraction, you need to identify that immediate complication is the I on the bottom of the fraction. And in order to eliminate the I on the bottom of the fraction, you're going to multiply the bottom of the fraction by its conjugate. And in order to compensate for that, you're also going to multiply the top of the fraction by its conjugate. Ultimately, you're multiplying the fraction you have by 1, which doesn't change the value of the expression. So to do this one out, I just need to multiply the top, which is 3 minus 1i, multiplied by minus 1 minus 2i. When you multiply out the top, it's just double brackets. It's the first term in the first bracket by the second bracket, second term in the first bracket by the second bracket. It multiplies fully to give you minus 5 minus 5i. The top of the fraction, when you multiply out those brackets, you just get minus 5 minus 5i. On the bottom of the fraction, you multiply minus 1 plus 2i by its conjugate. We know that when we're multiplying by a conjugate, the i's, the middle terms, are going to cancel each other out. And ultimately, you're going to end up with just a plus 5 here, which means the bottom of this fraction ends up as a 5. Now we can simplify this one. The real value is minus 5 over 5, which just works out as minus 1. The imaginary value is minus 5i over 5, which works out as minus 1i. So your final answer there is just minus 1 minus 1i. So that's really important. Divisibility comes up a good bit in this. If you're dividing one complex number by another, you multiply the top and the bottom by the conjugate of the bottom. Okay, in this video, I want to talk to you about the Argand diagram, or the Argand grid, and modulus. Okay, so as you'll notice, I've drawn a horizontal line and a vertical line. You're used to seeing this in coordinate geometry, where we're talking about the coordinate plane, which is an x-axis and a y-axis. The Argand diagram is similar, but it's not the same. The horizontal line in an Argand diagram represents the real values. So rather than representing the x values, it now represents the real values. And the vertical line in the Argand diagram represents the imaginary values. So horizontal, what you usually view as the x-axis, is now the real axis, and what you usually view as the y-axis is now the imaginary axis. And what I've done here is I've written out 6 different complex numbers, and we're going to plot each one. I've said that Z1 is 3 plus 2i. So to plot that, I see that the real value is 3, so I'd go across to 3, and the imaginary value is plus 2, so I'd go up to plus 2. So 3 plus 2i would be here. It's directly up from 3, and it's directly across from 2. So I want you to realize that essentially that's the same as if this was an x and a y axis. That's like plotting the point 3, 2, where x is 3 and y is 2. It's the same idea, except you can't write that down because it's not exactly the same. Z1 is 3 plus 2i, so that means the real is 3, the imaginary is 2, so that means that that one would be your Z1. With that in mind, I want you to just pause the video, plot my other 5 points, and I'm going to go through them now. Z2 is minus 2 minus 3i, Z3 is 1 plus 0i, Z4 is 0 plus 1i, Z5 is 4 plus 2i, and Z6 is 4 minus 2i. So just pause the video and plot those few points now. So Z2 is minus 2 minus 3i. The real value is minus 2, the imaginary value is minus 3. So that means Z2 will be here, directly below minus 2 and directly across from minus 3. Z3 is 1 plus 0i. That means that the real value is 1 and the imaginary value is 0. That means it's on the real axis. So I can just plot it here on the real axis. That's Z3. Now Z4 I wrote down as 1i, just 1i. You should realize that the implication there is that it's actually 0 plus 1i, which means the real value is 0, the imaginary value is 1, which means I have to plot Z4 on the imaginary axis. Z5 is 4 plus 2i, which means that the real value is 4 and the imaginary value is 2. Which means I'm directly above 4 and I'm directly across from 2. And I could label that one as Z5. Now the last one I gave you was Z6 is 4 minus 2i. So in this case that means the real value is 4, the imaginary value is minus 2. So I'm directly down from 4 and directly across from minus 2, and I can label that's my Z6. So plotting points on an Argand grid is relatively straightforward. Now we need to talk about getting the modulus of a complex number. Okay, now that we have a grasp of the Argand grid, we can talk about the modulus. Supposing I gave you a question that said if Z1 is 3 plus 2i, find the modulus of Z1. So these are vertical lines on either side of Z1. These are known as modulus lines. Usually an exam question won't actually say this at all. It will just say if Z1 is 3 plus 2i, find, and it'll give you that. You need to realize that that means the modulus. Now it's really important that you realize that this is relevant to our Argand grid. In the Argand grid, I've plotted my complex number Z1. The real value is 3, the imaginary value is 2, so I know that Z1 is roughly there. The modulus refers to the distance between the complex number and the origin. So if I ask you to find this, it means find the modulus. In other words, it means find the distance from 3 plus 2i to 0 plus 0i. 0 plus 0i would be the origin in an Argand grid. So I've derived it for you here. I've dragged it out a little bit here. This one, let's do it the long-winded way, and then we can do all the other ones more straightforward. To find the modulus of Z1, it's very simple. You could view it as it's just the distance from 3 plus 2i to 0 plus 0i. Now you know from junior cert coordinate geometry or leaving cert coordinate geometry, to get the distance between 2 points, we always say it's the square root of x2 minus x1 squared plus y2 minus y1 squared. So we can do this the same way. What I've done is I'm viewing my 0 plus 0i. If I'm trying to get the distance from 0 plus 0i to 3 plus 2i. So I could view x1 as 0 and x2 as 3. I could view y1 as 0 and y2 as 2. So I'm just labeling them x1, y1 and x2, y2. If you plug into your distance formula there, it just works out as 3 minus 0 squared plus 2 minus 0 squared. So when you're getting the modulus, the x1 and y1 will always be 0, which means you don't actually need to bother putting in the modulus at all. You don't have to bother putting in the zeros at all. So getting the modulus of Z1 works out as the square root of 3 squared plus 2 squared, which ultimately, if you plug that in, you end up with the square root of 13. So your final answer there would be that the modulus of Z1 is equal to root 13. So it comes directly from the distance formula that we use in junior cert. However, you don't have to think of it like that. It's much easier. You can just think the modulus of any complex number is just the square root of a squared plus b squared. Because ultimately all you're ever going to end up with is 3 minus 0 or 2 minus 0. What I'm referring to is a there. A refers to the number at the start, the real number at the start, in this case 3. B refers to the number in front of the I, in this case 2. So in fact, in the leaving cert, if you were asked for the modulus of Z1, you would just say the modulus of Z1 is the square root of a squared plus b squared. Or in other words, the modulus of Z1 is the square root of 3 squared plus 2 squared. You plug that into your calculator and the modulus works out as root 13. So you don't actually have to drag that out in the leaving cert. You can just go straight from that. Now that's not in your log tables, so you do need to learn that the modulus of a complex number is the square root of a squared plus b squared, where a refers to the first number and b refers to the number in front of the I. So with that in mind, I'm going to give you a few questions, and in each case I want you to find the modulus. Okay, so I'm going to give you Z2 as minus 2 minus 3i, Z3 as 1 plus 0i, and Z4 as 4 minus 2i. And I want you to find the modulus of Z2, the modulus of Z3, and the modulus of Z4. Now, you don't have to draw a diagram to find the modulus. I only use the diagram in order to explain that the modulus is the distance from the complex number to the origin. In each case, you just need to sub in to the square root of a squared plus b squared. So I want you to pause the video now, try these 3 questions, and work out the 3 different moduli. The first one I asked you to get was to get the modulus of Z2, where Z2 is minus 2 minus 3i. In order to get the modulus of a complex number, it's the square root of a squared plus b squared, where a refers to the number, the real number, and b refers to the real number in front of the I. So in this case, the square root of a squared plus b squared will be the square root of minus 2 to be squared plus minus 3 to be squared. Minus 2 by minus 2 is plus 4, minus 3 by minus 3 is plus 9. And 4 and 9 add up to 13. So the modulus of Z2 is the square root of 13. Remember, that means we've worked out that the distance from the complex number Z2 to the origin is the square root of 13. Okay, so secondly, I asked you to find the modulus of Z3, where Z3 is 1 plus 0i. So obviously in this case your A is 1 and your B is 0. So the modulus will be the square root of 1 squared plus 0 squared. 0 squared is just 0 and 1 squared works out as 1. So I know the modulus of Z3 is the square root of 1 and the square root of 1 is just 1. So your final answer there, the distance from Z3 to the origin is just 1. The fourth one was to get the modulus of Z4. Z4 is 4 minus 2i. And in order to get the modulus of a complex number, it's the square root of a squared plus b squared. Clearly in this case, the a value is 4 and the b value is minus 2. 4 squared is 16 and minus 2 squared is 4. 16 plus 4 works out as 20. So I can say that the modulus of Z4 is equal to the square root of 20. Now obviously depending on what way the question is worded, you might have to write that as 2 root 5 or you might have to write it into decimal places. It obviously depends from question to question what format to leave your modulus in. Now that we've explored modulus and we've explored conjugate, we need to start looking at questions where we have to use the modulus and the conjugate together. Okay, so we've studied almost everything to do with rectangular form at this stage. So now we need to look at questions where we're dealing with modulus and conjugate in the same question. Supposing I told you Z1 was 3 plus 2i, Z2 is minus 6 minus 4i, and Z3 is minus 1 minus 2i. With that in mind, you might be asked to investigate something like this. So I'm going to do this as an example and then give you 3 questions to do. First of all, we're asked to investigate if the modulus of the conjugate of Z1 multiplied by Z2 is equal to the modulus of the conjugate of Z2 multiplied by Z1. So individually we can do each one of these, but it's important because we have to do it in a specific order. So we have to simplify out the left hand side fully, simplify out the right hand side fully, and investigate if we're going to end up with the same thing on the left as on the right. So I think our best bet here is to just deal with only the left hand side first and then deal with only the right hand side. So in the likes of these questions, it's just important that you do them in the right order. I've been asked to find the modulus of the conjugate of Z1 multiplied by Z2. So what you need to do here is the first thing you need to do is you need to work out what's inside the modulus signs. You need to work out what the conjugate of Z1 multiplied by Z2 is. You get that as a complex number and then you get the modulus of that. So I've labelled my steps as 1, 2 and 3 here. The first thing that we need to do is we need to find what is the conjugate of Z1. If Z1 is 3 plus 2i, remember this horizontal line above Z1 means conjugate. So the conjugate of Z1, if Z1 is 3 plus 2i, you just change the sign in front of the I, so it becomes 3 minus 2i. Now that you know the conjugate of Z1, we can work out what Z1 multiplied by Z2 is. Sorry, the conjugate of Z1 multiplied by Z2 is. So that is you're multiplying 3 minus 2i by minus 6 minus 4i. That's just double brackets. It's the first thing in the first bracket by the second bracket, second thing in the first bracket by the second bracket. When you multiply this out, coincidentally the middle terms actually cancel and the i's actually cancel out, and you're left with minus 26 plus 0i. So I've worked out at this stage that the conjugate of Z1 multiplied by Z2 is minus 26 plus 0i. And ultimately on the left hand side, I was asked to find the modulus of this, the modulus of minus 26 plus 0i. Remember, to get the modulus, it's the square root of a squared plus b squared, where a is the real number and b is the number in front of the I. So in this case, the modulus of the conjugate of Z1 by Z2 is actually just the modulus of this complex number, which works out as the square root of minus 26 squared plus 0 to be squared. And if you plug that into your calculator, it works out as 26. So the left hand side simplified fully in this case is 26. I now need to do something similar with the right hand side and investigate. Basically, I want to investigate if I'll get the same answer as I got for the left hand side. Okay, so the right hand side is similar enough. I was asked to get the modulus of Z1 by the conjugate of Z2. I multiply the conjugate of Z2 by Z1 and then I get its modulus. So the first thing we need to do is identify what the conjugate of Z2 is. If Z2 is minus 6 minus 4i, then the conjugate of Z2 is minus 6 plus 4i. All I did there was I changed the sign of the number in front of the I. Now the second step is I need to find what Z1 multiplied by the conjugate of Z2 is. In other words, I need to multiply 3 plus 2i by minus 6 plus 4i. If you multiply that out, once again, in fact, the middle terms cancel again, and you end up with minus 26 plus 0i. So Z1 multiplied by the conjugate of Z2 works out as minus 26 plus 0i. And I was asked to get the modulus of that complex number. To get the modulus, it's the square root of a squared plus b squared. In this case, a is minus 26, b is 0. So I sub in, I get the square root of a squared plus b squared. It works out as the square root of minus 26 squared plus 0 squared, which ultimately works out as 26. So the right hand side is worked out as 26 as well. So now we just need to, obviously the left hand side and the right hand side are equal to each other, but we just need to conclude this question to make sure we get the full marks. If you don't conclude properly, you can often lose 3 marks. So ultimately I asked you to investigate if the modulus of the conjugate of Z1 by Z2 is equal to the modulus of the conjugate of Z2 by Z1. When I worked out the left hand side, it worked out as 26. When I worked out the right hand side, it worked out as 26. Clearly 26 is equal to 26, so I can tick it and just say that it's true. So with that in mind, I want to move on and give you a few questions to try. I've given you Z1, Z2 and Z3 here, and I'm asking you to investigate if the conjugate of Z1 multiplied by the conjugate of Z2 is equal to Z1 multiplied by Z2. So you work out the left hand side and then work out the right hand side. I want you to work out if the conjugate of Z3 multiplied by Z3 and then get the modulus of that is equal to the modulus of Z3 to be squared. So to get Z3 squared, obviously you just multiply minus 1 minus 2i by minus 1 minus 2i. In the third one, I want you to get the modulus of Z3 and multiply it by the modulus of the conjugate of Z2. And investigate if that is the same as the modulus of the conjugate of Z2 by Z3. So in each case, you should work out the left hand side and then work out the right hand side and investigate. Make sure you don't forget to conclude. So pause the video now and attempt these 3 questions and we'll go through the solutions. When you go step by step in these questions, they're relatively straightforward. The first one I asked you to do was investigate if the conjugate of Z1 multiplied by the conjugate of Z2 was equal to Z1 multiplied by Z2. If Z1 is 3 plus 2i, then the conjugate of Z1 is 3 minus 2i. If Z2 is minus 6 minus 4i, then the conjugate of Z2 is minus 6 plus 4i. Again, all I'm doing there is changing the signs in front of the i's. So to work out the left hand side, it's the conjugate of Z1 by the conjugate of Z2. Or in other words, 3 minus 2i by minus 6 plus 4i. I've multiplied this one out here, and my final answer ends up as minus 10 plus 24i. If you do on the right hand side, I need to multiply Z1 by Z2. Z1 is 3 plus 2i and Z2 is minus 6 minus 4i. If you multiply that out, you end up with minus 10 minus 24i. So the left hand side is minus 10 plus 24i, the right hand side is minus 10 minus 24i. So to conclude this and get the full marks, you should say, right, minus 10 plus 24i, which was the left hand side simplified fully, is not equal to, so an equals with an x through it, to indicate that it's not equal to minus 10 minus 24. One of them has a plus 24, one of them has a minus 24. So they're not equal to each other, and I can conclude that it's false. That the conjugate of Z1 by the conjugate of Z2 is not equal to Z1 by Z2. Part B here was a little bit more difficult. Part B here was a little bit more involved. It said to investigate if Z3 by the conjugate of Z3 and then get the modulus of that is equal to the modulus of Z3 squared. And we were told that Z3 is minus 1 minus 2i. So the first thing, so what I'm doing here first is I'm only dealing with the left hand side. In order to work out the left hand side, the first thing you should identify is that you need to work out the conjugate of Z3. The horizontal line above Z3 indicates conjugate. So the conjugate of Z3 is minus 1 plus 2i. You just change the sign of whatever was in front of the I. Here it was a minus, so it becomes a plus. The second thing you need to do is then to multiply the conjugate of Z3 by Z3. Or in other words, multiply minus 1 plus 2i by minus 1 minus 2i. First thing in the first bracket by the second bracket, second thing in the first bracket by the second bracket. As always, we're multiplying by conjugates, so your imaginary values in the middle actually cancel each other out. And this one ends up as 5 plus 0i. So I know that the conjugate of Z3 multiplied by Z3 simplified fully is 5 plus 0i. The third thing we need to do then is to get the modulus, because now we need to accommodate for the fact that there was these modulus lines. To get the modulus of a complex number, it's the square root of a squared plus b squared. In this case, a is 5 and b is 0. So it's the square root of 5 squared plus 0 squared, so it just ends up as 5. So I can say that the left-hand side simplified fully is 5. Now I just need to do this something similar on the right-hand side and simplify the right-hand side fully. Investigate if it's equal to 5. Okay, so what I've done here is I've simplified out the right-hand side. The right-hand side is the modulus of Z3 to be squared. So the first step here is we need to work out what is Z3 squared. Z3 squared refers to Z3 multiplied by itself. So that's minus 1 minus 2i multiplied by minus 1 minus 2i. When you multiply this out, it simplifies fully to minus 3 plus 4i. So Z3 squared is minus 3 plus 4i. Once you have that, we can now work out the entire right-hand side. So the second thing I need to do is get the modulus of Z3 squared. I now know that Z3 squared is minus 3 plus 4i. So to get the modulus, it's the square root of minus 3 squared plus 4 squared. I take the real number and then I take the real number that's in front of the I. So minus 3 and 4. Minus 3 squared is 9 and 4 squared gives me 16. 9 and 16 adds up to 25, so the square root of 25 works out as 5. So now that I've worked out the left-hand side fully and the right-hand side fully, I can make my conclusion. In order to ensure you get the full marks here, you need to finish off with a solid conclusion. So I would finish off by, I had to investigate if this was equal to this. I've worked out the left-hand side fully, it worked out as 5. I've worked out the right-hand side fully, it also worked out as 5. Clearly 5 is equal to 5, so I can put a tick beside it and say that it's true. I've managed to prove that the left-hand side was equal to the right-hand side. Okay, so the third one I gave you here was to investigate if the modulus of Z3 multiplied by the modulus of the conjugate of Z2 is equal to the modulus of the conjugate of Z2 multiplied by Z3. So obviously we need to just deal with the left-hand side first and then deal with the right-hand side. We were told that Z2 was minus 6 minus 4i and that Z3 was minus 1 minus 2i. If I'm just dealing with the left-hand side first, the first thing I should do is work out the modulus of Z3. The modulus of Z3 is the square root of minus 1 squared plus minus 2 squared, because minus 1 is my A and minus 2 is my B. If you plug that into your calculator, it works out as the square root of 5. The second thing we need to do is get the conjugate of Z2 first. I need to work out the modulus of the conjugate of Z2, so obviously the first thing I need to do is work out what is the conjugate of Z2. If Z2 is minus 6 minus 4i, to get its conjugate we just change the sign. Instead of a minus 4i, it becomes a plus 4i. So the conjugate of Z2 is minus 6 plus 4i. I now need to get the modulus of that. The modulus of the conjugate of Z2 is the square root of minus 6 squared plus 4 squared. If you plug that in, you get the square root of 52. Now that I know the modulus of Z3 and the modulus of the conjugate of Z2, I just multiply them by each other. The square root of 5 multiplied by the square root of 52 works out as 2 root 65. That's the left-hand side simplified fully. Let's work through the right-hand side now and investigate if the right-hand side works out as the same thing. So the right-hand side I do in a completely different order. The first thing I need to do is work out what is the conjugate of Z2. If Z2 is minus 6 minus 4i, then the conjugate of Z2 is minus 6 plus 4i. The second thing I need to do is to multiply Z3 by the conjugate of Z2. Or in other words, minus 1 minus 2i multiplied by minus 6 plus 4i. Double brackets, so I just multiply it out. First term in the first bracket by the second bracket, second term in the first bracket by the second bracket. If you multiply it out fully, Z3 multiplied by the conjugate of Z2 works out as 14 plus 8i. Once I've worked out that, I can now work out the modulus of Z3 times the conjugate of Z2. So I'm looking for the modulus of this complex number, which is the square root of 14 squared plus 8 squared. I'm getting the 14 because 14 is the real value and 8 is the real value in front of the I. And if you plug that into your calculator, it works out as 2 root 65. So the right hand side simplified fully is 2 root 65. Now I need to make my conclusion to ensure I get the full marks. So to conclude, you should do something like this. You rewrite your question. When I simplified the left hand side fully, it worked out as 2 root 65. When I simplified the right hand side fully, it worked out as 2 root 65. So clearly the left is equal to the right, so you can put a tick beside it and say that it's true. The left hand side is equal to the right hand side. So that's all we're going to look at today in class. And what I want you to do for next week is I want you to try these 3 questions for homework. 2019 paper 1 question 2, 2018 paper 1 question 2, and 2017 paper 1 question 2. Be aware that some of them are already available on the website. If you go into the solutions tab, I think 19 and 18 are already available on the website, and I'll make this one available for you by next week.